Swayam Prabha. Digital India. Educated India.
Today I am going to discuss about the impact of two bodies. We will discuss the direct and oblique impact. Although till now we have studied the kinematics of particle, and also we have discussed the kinematics of the bodies. How now our assumption has been that bodies are perfectly rigid, that means they cannot deform, but however that when two bodies impact there is some amount of deformation. We will not study the deformation of the two bodies, but at least appreciate the concept that that two bodies they are when they collide, then there is some amount of deformation, and because of that both the bodies experience force. This point we will at least understand, and then based on that that these bodies will affect each other. So we will not really discuss those points, that how much time it takes for collision of two bodies. We will assume that collision is instantaneous. As soon as the bodies impact, they separate out, or if they do not separate out in some cases, they remain this thing, but impact process finishes within no time. That is our assumption, but we have to understand that this is idealization, because in most of the cases this assumption may be justified. That's why that we are going to do that. Although in the later classes you may study about the elastic and maybe elastoplastic contact also, those things. But here another thing is that when the two bodies are deforming, obviously they will be of some finite size, but in here we will not bring the size effect into the picture, and we will assume that as if there is an impact of two bodies of a very small size. So therefore they will be treated like a particle also. Now let us see that what is the process of impact. Impact refers to the collision between two bodies and is characterized by the generation of relatively large contact forces that act over a very short interval of time. So in the collision two bodies make contact, and then the large amount of contact force is generated. If a body A applies some force on body B, then body B also applies the same amount of force on body A. There are mainly two types of impacts we will study: direct central impact, and we will also study oblique impact. Now what do we mean by direct impact? When the suppose the two bodies are making contact, then and we draw a normal line, that means they are normal to the contacting surface. If we draw a line and the bodies are having velocity along that normal line, which is common normal of the two bodies, then that will be called direct impact, and in that case the velocities also basically are in one line. So one dimensional equations can describe the motion, and the central impact means that the mass centers are in the same line. Now if you make a impact something like this, that there is a this one, that body, and you are doing like this, that suppose this rod is hanging and one bar comes and hits this one. So this velocity of this rod is like this, the velocity of that this point on the rod will also be in this direction. However, the mass center is different. So therefore, although this impact is direct, because common normal is this and the velocities are along the common normal, but you know that it is these mass centers are not in the same line. So this can be called direct non-central impact. That also one can understand easily, but right now we will not be discussing about that. Now what happens, that suppose two particles are making contact. Just see this figure, that particle of mass m1 is going to collide with the particle of mass m2. Okay, we can say small balls instead of a particle. Now velocity of v1 is greater than v2, that means v1 is greater than v2, velocity of mass m1 is more than velocity of mass 2. Before impact, this is the situation. Then after that, since this velocity is more than velocity of v2, so body of mass m1 catches body of mass m2, and then there is a impact. Now when there is a impact, what happens, that this mass m1 is moving in that direction, it tries to move in that direction, so it deforms the layers of that body m2. So there is a deformation, and now you know that Hooke's law of elasticity, that stress is proportional to strain, that when you apply the stress, then there is a strain generated, and it is like something similar to spring type of thing. Although here what happens, the situations are very complicated because the contact area also keeps on changing, but you can appreciate that if we draw a force versus time diagram, this is force here and this is time. So in the beginning, just when the body has touched another body, that time the force is 0. Then after that, force tries to increase, it is increasing, and after that that this keeps on increasing, and this and more and more deformation starts taking place. Then what happens, that as the that the more and more deformation is taking, so that means a force is being applied on body m2, so therefore its velocity is increasing, from v2 it is increasing. At the same time, the body m1 faces resistance, because you know that m2 applies the force in the opposite direction, so therefore its velocity keeps on decreasing, and gradually that a point comes, at that point the velocity of both the bodies becomes same and the force has reached maximum. That time the velocity of both is same, that is v0. So the condition also comes that there is both the bodies are moving with the same velocity, but then after that body m1 cannot press body m2. But if there is a elasticity, because of elasticity there can be one situation that okay, body m1 has that pressed it to maximum extent, and now both the bodies are moving at the same velocity, so therefore it is not applying the force, and it keeps on moving with that velocity. But usually what will happen, that after that this body, that there is some elasticity. So body M2 will try to come back to the original position, and even body M1 will have tendency to go to the original position, that means recover from the deformation. So therefore it will start applying the force in the opposite direction. Now since it will apply the force in the opposite direction, that so that contact force will start decreasing like this, and then finally the contact force will become 0 at some point. So this is the situation. So that contact force increases, reaches some maximum, and then it comes down to 0. The exact profile may be different, and it is not that necessary. This is just a schematic diagram showing that actually what may be going on. So now once in that process, now when that body M2 was applying the force on M1 in the opposite direction, so since they both were now moving at the same velocity V0, so now the velocity of that M1 will decrease and it will become V1 prime, and simultaneously the velocity of M2 will increase, because if M2 is applying a force on M1, M1 applies force on M2. So therefore during that process the velocity of this will increase, and therefore velocity of particle M2 will become V2 prime, and now in this situation after impact V1 prime is certainly less than V2 prime. So in all these situations you will see that when the two bodies will collide and one body is moving with greater velocity, it contacts the another body, then after impact when they separate out, then the velocity of first body which was more will be necessarily less now, and the another body's velocity will be more. That situation will be there after impact. So this is the process which goes on inside this one, and so let us say, okay, so let me just describe it again. Consider the collinear motion of two spheres. We have considered here spheres of masses M1 and M2 travelling with velocities V1 and V2. If V1 is greater than V2, then collision occurs with the contact forces directed along the line of centers. So contact forces are directed along the line of centers, that means along the normal, and therefore this condition is called direct central impact, because the mass centers are in the same line, and collision velocities are also taking along the common normal. So this condition is called direct central impact. Now following initial contact takes place, then a short period of increasing deformation takes place. Deformation keeps on this one until the contact area between these spheres ceases to increase. Okay, because after that that velocity, both the velocities have become equal. So naturally that contact area now will cease to increase. That is the situation. Now at this instant both these spheres are moving with the same velocity V0. When the contact area has ceased to increase, that means contact area between the two spheres, it is like this. So in the beginning there is like a point type of things, that now that point is changing, and contact area something like bodies have deformed, and after deformation they become something like this. So this is the type of thing, contact area has increased. Like that contact area keeps on increasing, but that contact area ceases to so the increase, and then by that time the force has reached the peak. After that the force cannot increase, because force is increasing because the body with greater velocity is pressing the body with smaller velocity, and contact area is keeping on increasing. The force will be proportional to the contact area, that is also there. So therefore now at some instant both the bodies have reached velocity v0. During the remainder of contact, a period of restoration takes place, that is called restoration occurs, during which the contact area decreases to 0. Now the contact area will slowly decrease to 0. Okay, that is in the case of elastic, but you know sometimes the elasticity cannot be fully recovered, that is another thing. Then certain amount of plastic deformation will also be present, but in many cases there is a sufficient amount of elasticity. So in this period, mass m2 is applying a force on m1 opposite to motion, hence the velocity of mass m1 keeps on decreasing till the spheres separate out. That because once the force has become 0, then you know that they separate out, because there is no force acting on that, and the another body has picked up the velocity. So therefore it will separate out, because another velocities are different. Now because of Newton's law, the particle m1 applies a force on m2 along the direction of motion, hence the velocity of m2 keeps on increasing. Thus after the impact, velocity of m1 will be always lower than the velocity of m2. That is the point has to be noted out. In the elastic impact, the original shape of the bodies are restored. In the inelastic impact, the shapes of bodies are not restored. In the perfectly plastic impact, bodies remain in contact and do not separate out, because there is nothing to no force is applied to decrease the area. So therefore they keep moving with the common velocity, and there is that is the plastic deformation. So therefore they do not separate out. That is what happens in the perfectly plastic impact. Now we apply the law of conservation of linear momentum. If we consider, although there is a force on one particle and our body sphere, similarly there is another force on the another sphere or body, but if we consider them together, then together there is no external force acting on these bodies. That force is internal, because one body applies a force on the other bodies also applies the equal amount of the force. So net outside force is 0. Okay, we assume that friction is not playing any role, and in fact what happens, the contact duration is so small in most of the cases that tremendous amount of that force is generated. Compared to that, small amount of friction force is often negligible. So therefore we can apply the law of conservation of momentum to this one, law of conservation of momentum, linear momentum. Now linear momentum first, so let us say initially the velocity of one body is v1 and the velocity of other body is v2, and after that it becomes v1 prime and v2 prime respectively. The first body attains the velocity v1 prime, second body is at v2 prime. This is after the impact. We are not considering that small duration when really the bodies are that touching each other, or that they are moving with the common velocity. That we are not considering, only that well before the impact and well after the impact. The above these, so we get the equation m1 v1 plus m2 v2 is equal to m1 v1 prime plus m2 v2 prime. This equation contains two unknowns to be determined, v1 prime and v2 prime. Therefore we must have two equations. Here we are having only one equation, so we cannot solve this thing. We need another this one. So one more equation is needed. For this purpose we define the coefficient of restitution. By that we can define that situation. We have to that means another equation has to come from, this is momentum equation. So another comes from the kinetic energy consideration. If the body is perfectly elastic, then the kinetic energy must remain conserved. So we can write that equation also. So we will have that one equation for the kinetic energy, initial kinetic energy. Then after that we will have another final kinetic energy we will have for kinetic energy also. Therefore, and by that, otherwise we must know that how much fraction of the kinetic energy has been lost. By that also we can find out. So therefore, that is so one way of doing that. But instead of doing that, the same thing in a slightly different manner we describe. That means loss in kinetic energy can be indicated by one quantity called the coefficient of restitution E. This coefficient of restitution E is the ratio of the magnitude of the restitution impulses to the magnitude of the deformation impulses. That is the thing. So by this quantity, this is a very important quantity. You know, see, suppose you say E is equal to 1, that means the kinetic energy is conserved. Okay, there is no loss of kinetic energy. If you say E is equal to 0, then there is a significant amount of loss of kinetic energy. If you say E is equal to 0.5, then also there is some loss of kinetic energy. At E is equal to 1, there is no loss of kinetic energy, that is there. But we do not define this one, we define the coefficient of restitution in a different way. Ultimately it reads the same observation, we can relate these to kinetic energy also. But the thing is that here it becomes the coefficient of restitution E is the ratio of the magnitude of the restitution impulses to the magnitude of the deformation impulses. What is the meaning of that restitution impulse and deformation? See, what impulse means force into time, product of force into time is called impulse. So we integrate, that means if we integrate f dt, or we draw that force versus this diagram, time, force versus time diagram. Now it is like this is increasing, and after that it is this one. So up till this point here up to this point there is a deformation process, because more that you know that body 1 is pressing the body 2 and contact area is increasing. After that it reaches a point, that means top point, and then it bodies try to restore their original shape. So this is the restoration period or restore. So if we take the area up to this f, that means f dt integrated, this will be called deformation impulse, and after that restoration period is there. If we take the area of this area, this will be called from here to here, that means again you just see this area like this up to this will be called restitution impulse. So if we take the ratio of this area to that area, then we get coefficient of restitution. So in the if the contact is perfectly elastic, in that case the deformation impulse will be equal to the restitution impulse. Whatever that you know that impulse you have applied, same amount of impulse is getting recovered, and therefore the ratio becomes 1. Otherwise you know ratio will be less than. If you do not allow bodies to restore, that means only it is rising, reaches the maximum contact area, but then it is not separating out. In that case, naturally, like if this is the situation that this is f and this is t, and if it has increased but it is not coming down after that, so therefore you have restitution impulse is 0, therefore E will be 0. And the one point has to be noted that you see what is this F? This F is the force on which body it is. You can consider the force on both the bodies, because if body A is experiencing the force, the other body is also experiencing the same amount of the force. Net force anyway is 0, and this is what that it happens. So this is the thing, and you know that here, if you know that, so in that another case, that if you know it keeps on applying the force and the restitution. So one case I have shown like this, and in another case if the restitution doesn't take place, so naturally that bodies will make contact, the force increases, and after that you know that this may become this one, that 0, that means impulse may be 0 and it may just come down, force may come down without making any change in the area. Okay. Now here, so let us see it carefully. During deformation period, M1 and M2, these are the two bodies. So body M1 is pressing body M2. So therefore body M2 is applying a force on body M1, and that force is given by Fd. So therefore I am showing the direction of the force Fd on M2, that is applied by body M1. In turn, body M2 is applying a force on M1, and that is in this direction. So this is the situation. The force acting on each particle is Fd. Now during restitution period, the force acting on each particle is Fr. Then also the force is actually in the same direction, because this is M2, and then after that you know that this is M1. So that during restitution period also bodies will experience the force, that will be Fr. Now for particle 1, if we consider just the particle 1, we can consider any one particle. So we consider particle 1, the coefficient of restitution is given as E is equal to T0 to T. What is T0? When the T0 is that time at which bodies have started moving with the same velocity. So force has already reached maximum, and this is like this. So this is, if you know, bodies are deforming like this. This is time and this is F. So this will be T0, and this is what that. So from 0 to T0 deformation takes place, and we have E is equal to T0 to T, and then after that you have that Fr into dt. So therefore this becomes like this. So T0 to T Fr dt, that force is keeping on increasing, and it has become like this, and divided by 0 to T0. So this is T0 to T, means this period, T0 to T, that is restoration period. And another one will be, now you can see that if the bodies will not be able to recover, then that time they will not be able to apply the force also. So Fr will become 0, and therefore this will become obviously that that upper part will become 0, and then it is 0 to T0 Fd dt. Now at this stage you can apply the impulse momentum equation. Change in the momentum is equal to the impulse. So during this period, that means T0 to T, the velocity of the body 1 changes from V0 to V1 prime, and we see that we have taken the direction of V1 prime assuming like this, but the force is acting in this direction, so they are in the opposite direction. So to be consistent, we will take this as minus V1 prime. So therefore what happens, the final momentum is M1 minus V1 prime minus V0. and this will be 0 to t0 fd dt, that is m1 minus v0, because here also the final velocity is minus v0 minus v1. So therefore we will be getting this will be equal to v0 minus v1 prime and divided by v1 minus v0. So we get one expression for E, but although at this stage we know that actually v0. So therefore just we have written the expression like this. Now here from 0 to t0 deformation takes place, and from time t0 to t restoration takes place. v0 is the velocity when both the particles are moving at the same velocity. Similarly, we can have similar type of equation for particle second particle also, and for second particle we will be having E is equal to v2 prime minus v0 divided by v0 minus v2. So both the things are there. So both equations, in this we can eliminate v0 and we can get the expression for E like that. In writing these equations we have taken care to write the change in momentum in the same direction as the impulse. The time for the deformation is taken as t0 and the total time of the contact is t. Now if we eliminate v0 between the two expressions for E, then between the two expressions, now then the expression for E becomes E is equal to v2 prime minus v1 prime divided by v1 minus v2. That means it is the relative velocity of separation v2 prime minus v1 prime, body 2, final velocity of body 2 and velocity of body 1. So you see that both the have started moving with a different velocity and they separate out with this relative velocity. So this is called relative velocity of separation, other is called relative velocity of approach v1 minus v2. So this will be v1 minus v2. So the ratio of these two quantities, that is a positive quantity, that is called coefficient of restitution, and that may range between 0 to 1. So this is the thing. Now do you know what is the value of v0? Can we compute the value of v0? It can be found easily by applying the law of conservation of momentum. That means we can say m1 v1 plus m2 v1 m2 v2, in fact this is v2 is equal to m1 plus m2 into v0. So we have m1 v1 plus m2 v2 is equal to m1 plus m2 into v2. Thus we find out v0 is equal to m1 v1 plus m2 v2 divided by m1 plus m2. That way we can find out anyway the intermediate velocity v0 which occurs for a short duration of time. Now the value E is equal to 1 means that the capacity of the two particles to recover equals the tendency to deform. That means this is the thing. So this condition is one of elastic impact with no energy loss. Now we have not talked about the kinetic energy, but now in this case we will show that how there is no energy loss in this case. Let us find out the kinetic energy before and after impact for an elastic impact. So we have equations, like we have equation for momentum conservation. We have m1 v1 plus m2 v2 is equal to m1 v1 prime plus m2 v2 prime. So this is thing, as E is equal to 1, v2 prime minus v1 prime is equal to v1 minus v2, because v2 prime minus v1 prime is what? It is the relative velocity of separation. v1 minus v2 is what? It is the relative velocity of approach. So this is v2 prime minus v1 prime is equal to v1 minus v2 and now from this we get V2 prime is equal to V1 minus V2 plus V1 prime. Hence we can write one as this momentum balance M1 V1 plus M2 V2 is equal to M1 V1 prime plus M2 V1 minus V2 plus V1 prime. We have substituted all these things, or we will say M1 V1 plus M2 V2 is equal to M1 V1 prime plus M2 V1 minus M2 V2 plus M2 V1 prime, or we take this portion this side M1 V1 plus 2 M2 V2 minus M2 V1 is equal to V1 prime M1 plus M2. This is the thing. Thus we get V1 prime is equal to M1 minus M2 into V1 plus 2 M2 V2 divided by M1 plus M2. So we get this equation. Hence V2 prime so therefore now hence V2 prime, because V2 prime is V1 minus V2 plus V1 prime, so V2 prime is V1 minus V2 plus M1 minus M2 into V1 plus 2 M2 V2 divided by M1 plus M2. So then after that we simplify this and we get something like this: M1 V1 minus M1 V2 minus M2 V2 plus M2 V1 plus M1 minus M2 V1 plus 2 M2 V2 divided by M1 plus M2. Or we write this like this: this is M1 plus M2 plus M1 minus M2 V1 plus M2 minus M1 into V2 divided by M1 plus M2. Now this is the expression for V2 prime. So we have expressions for V1 prime given by this equation 4, and then we have expressions for V2 prime given by this equation. Now therefore now we write the kinetic energy after impact, that is half M1 V1 prime square plus half M2 V2 prime square, and if we use the values of V1 prime and V2 prime from these equations 4 and 5 respectively, we get kinetic energy is equal to half M1 and V1 square, that means M1 minus M2 multiplied by V1 plus 2 M2 V2 divided by M1 plus M2 whole square, and this thing whole square on the top, then plus half M2 M2 minus M1 V2 plus 2 M1 V1 whole thing square divided by M1 plus M2 square. So this is the thing, and we have to do some algebra now to simplify that. That is half M1, and this will be M1 minus M2 square V1 square plus 4 M2 square V2 square plus 4 M1 minus M2 V1 V2 divided by M1 plus M2 square plus half M2 minus M1 whole square V2 square plus 4 M1 square V1 square plus 4 M1 minus M2 into M1 V1 V2 divided by M1 plus M2 whole square. So that expression you are getting, and then one has to adjust this to half can be taken as common. So half M1 V1 square if you take, you will get M1 minus M2 square plus 4 M1 M2 plus you get half is outside, totally outside of this, then M2 V2 square, then M2 minus M1 whole square plus 4 M1 M2 divided by M1 plus M2 square, and that is the thing, and then you get half here is equal to 4 M1 minus M2 into M2 V1 V2 plus 4 M2 minus M1 into V1 V2 divided by M1 plus M2 whole square, So this is this big expressions you are getting, and this is equal to half m1 v1 square m1 plus m2 square plus m2 v2 square bracket m1 plus m2 whole square divided by m1 plus m2 whole square, and if you simplify then this becomes half m1 v1 square plus half m2 v2 square. Thus we get half m1 v1 prime square plus half m2 v2 prime square is equal to half m1 v1 square plus half m2 v2 square. That means the final kinetic energy of the two particles is equal to the initial kinetic energy of the two particles. The kinetic energy of the particles or bodies change but combined thing remains same, in which case, in the case in which E is equal to 1, that we have demonstrated. So similarly we can of course demonstrate that when the bodies are making perfectly plastic contact, then the kinetic energies that get changed. So this is the thing. Now, so after describing these things, so it must be now clear that it is easy to solve the problems of direct central impact. There you have to write one equation for the variance of linear momentum. The other equation will come from the coefficient of restitution automatically, that is means v2 prime minus v1 prime is equal to E times v1 minus v2. So you will have two equations, so there will not be difficulty in solving the problem of two unknowns. See, with two bodies are colliding, mass m1 and with velocity v1 it is moving, and this another is m2 v2 is equal to m1 v1 prime plus m2 v2 prime. Now your goal is just to find out v1 prime and v2 prime. So now here it is like this, that one equation is this and the other equation is given by this v2 prime minus v1 prime is equal to E times v1 minus v2 is the same. This is the thing, because velocity of approach is v1 minus v2, velocity of separation is v2 prime minus v1 prime. So therefore this is the thing. So these E, value of E must be known. It is a property factor of so many things. It depends on the material, it depends on the size of the bars, it depends on the which velocities they are, you know, that making impact or collision. So like that this must be, but it will be given in a problem. So therefore this is given, so you have two equations and two unknowns, that is v1 prime and v2 prime. This can be easily solved. So that is the thing. So you need not write anything about the kinetic energy in this case. So this is first, this is the thing. So that way you can solve the problems of direct central impact. Now we will be discussing about the oblique impact problem. In this case the particles collide at certain angle, and that if they make contact, then the common normal is in some different direction. So in this case it is like this, that here the two bodies, like we have two spheres, now they are going here and there, now they may be moving with some inclination. So here that is the thing, like in this case okay, this body like in this case two bodies will make collision, and the situation will be like this, that there is a particle m1, there is a particle m2, both are moving. This is moving with the velocity v1, this is moving with the velocity v2. both make contact at this point, collide, and after that they separate. So, you know that when they make contact, this is the normal direction and this direction is the tangential direction. Now, this part, this it is making that angle theta 1 from this direction t, and this is making angle theta 2 from here. Similarly, that from the tangent direction, this particle m1 after the collision is making angle theta 1 prime, and this is making an angle theta 2 prime. So, therefore, this is v1 prime and this is v2 prime, this is m1, this is m2, and this is like that. Now, now the direction of the velocity vectors are measured from the direction of tangent to the contacting surfaces. So, they are, so this is the case of the oblique contact, because they are making contact at angle. So, these are the three situations here shown, A, B and C. Thus, the initial velocity components along the t and n axis are, we can write that, suppose you have v1, we can resolve them along the normal v1 n is equal to minus v1 sin theta 1, because it is coming downward. So, we have put a minus 1, and v1 tangential we are writing, say, if we say that minus v1 cos theta 1 in that direction. Similarly, v2n is the velocity, and that we have written minus v2 sin theta 2 and sin v2t is equal to minus v2 cos theta 2. v1 we have taken, see, it depends on the coordinate system, that whether you call that v1n positive or negative. Okay, if you take that for this particle, if you take upward direction as y, then it is like this. Now, this situation is shown. Now, states of three different situations are shown below. Now, for given initial condition of m1, m2, v1n, v2n, there will be now 4 unknowns. See, we have got 4 unknowns, namely, what are the 4 unknowns? v1 prime n, we must know the normal component of that, you know, both the velocity particles. What is this one? So, v1 prime n, and then similarly we will have tangential components are also unknown. So, v1 prime t and then v2 prime n and v2 prime t. Thus, you need 4 equations to solve that. Now, from where do we get 4 equations? If you do that to get 4 equations, there is no problem in solving this one. So, therefore, problem is solved. We just need 4 equations to find out 4 unknowns. What are those unknowns? Normal after the impact, because before the impact we must know the velocities. So, before the impact everything is known, masses are known, impacting velocities are known, at which angle they are going to make contact, that is also known, because they are going to, you know, that you can join the line of contact and you can find out that angle also. So, after the impact we must know the velocity. So, velocity has now 2 components. So, therefore, 2 particles, so total 4 components. So, 4 unknowns are there, or we can say v1 prime, v2 prime and theta 1 prime, theta 2 prime are the unknown. So, we have to get 4 equations. Now, first equation we get momentum of the system in the n direction. This gives m1 v1 n plus m2 v2 n is equal to m1 v1 prime n plus m2 v2 prime n. So, that means in n direction the momentum remains conserved, and that is what that you are getting. This is the thing, one equation, because they are impacting and the forces are applied normal to this one, although the forces are applied normal to. So, therefore, their velocities in the normal direction will change. However, that total net momentum remains conserved, and you get that this equation. So, this is one equation. How you will get the other equations? Now, in the second and third equations we get from this consideration, If there is a smooth contact, then the momentum of each particle is conserved in the t direction, or otherwise also that you know that if the particles are making contact, then the momentum, but when there is no impulse on either of the particles in the t direction like smooth contact, then in that case m1 v1 t is equal to m1 v1 prime t. That means no tangential velocity change occurs for particle A, and same thing is for particle B, means another particle also, that is m2 v2 t is equal to m2 v2 prime t. So v2 t is equal to v2 prime. These are the conditions. So otherwise if friction is there, then the situation becomes difficult. Now another condition is that, fourth condition is the coefficient of restitution as in the case of direct central impact. Now it is to be noted that the coefficient of restitution is defined as the ratio of the velocity of separation to velocity of approach. Now these velocities are always normal, not the tangential velocity. So we define with respect to that normal velocity. So the coefficient of restitution as in the case of direct central impact is the positive ratio of the recovery impulse to the deformation impulse. Hence, like in the case of direct impact, we get here also E is equal to V2 prime n minus V1 prime n divided by V1 n minus V2 n. So this is the thing normal. So we have got now 4 equations. See these 4 equations we have. One is the, in terms of this thing, normal momentum remains conserved. Then for 2 particles separately we have written that tangential this thing. Okay, and if friction is known, then we have to know that friction force etc., and by that we will find out the change in velocity. But here in a smooth contact we can easily find out, and 4th equation is given by this one. So 4 velocity components are found. Then once 4, so if we can find out 4 final velocity components, then we can determine angles theta 1 prime and theta 2 prime, and our problem is solved. So these are the this one. So this method can be employed. Now I give one example of oblique contact. Now supposing 2 bars of the same size and mass collide with the velocities of approach shown. So 2 bars of same size are colliding with the velocity shown for a coefficient of restitution of 0.8. What are the final velocities after they part? That question is there. So what happens that body is going with 5 meter per second. Now other body is coming at 10 meter per second. This is the 10 meter per second, and then it has got this velocity is at 45 degree to the common normal. In that case, resolve it into 2 components. So one component, that normal component is 7.07 this one meter per second. Normal component is also 7.07 meter per second, like that. So then now you apply the conservation of momentum along the line of impact, so that 5 into mass, if mass is same, so 5 m minus 7.07 m in the beginning, that this is velocity, this velocity is in opposite direction, so minus we have sign, and is equal to m1 v1 t plus m2 v2 t, r, that normal, we say that along the normal direction, so let us use the symbol n here, and this is also we have coefficient of restitution is 0.8 given. So therefore 0.8 is equal to v2n minus v1n and divided by, in the beginning, minus 7.07, because this is minus 7.07 and the other is minus 5. So because these are so minus 5, so velocity of approach, they are approaching towards each other with, you know, that 7.07 plus 5. So, it gets added. So, therefore, we have this is V2 V1n plus V2n is equal to, from the first momentum conservation equation, conservation of momentum, this is actually momentum, minus 2.07, and similarly here you get V2n and V1n is equal to minus 9.656, and solving this we get V2n is equal to 5.863 and V1n is equal to minus 7.933. We have obtained like that. And V2t, these things V1t and V2t remain same. So, therefore, final velocity of that one particle can be written as minus 7.933 I in the I direction, and the other one is actually 5.863 I plus 7.07 j in that direction, because this is that that 7.07 component remains unchanged and only this part we have added in the I direction. So, this is what the velocity. So, by solving the 4 equations we have been able to solve this problem. So, this is these are the basic concepts about the direct and central impact. Now, let me just tell you simple things and simple problems. Let us say we discussed. Now, okay, some problems, like suppose you want to show that in the case of the contact of two bodies, okay, which with perfectly plastic impact E is equal to 0. In that case, V2 prime minus V1 prime will be 0. That means both the velocity moves with the same velocity. So, therefore, what happens that in this case you get mass into that suppose the two particles are this one, let us say two particles are of the same mass. Okay, just to simplify the situation, I am taking the two particles of the same mass. In that case, it will be initially the velocity may be V1 plus V2, M1 M, this is M, and finally the velocity becomes, let us say, V0, same velocity. So, this will become mV0 plus mV0, all V0 then will become basically V1 plus V2 by 2. So, in the beginning you are having the kinetic energy half m1 V1 square plus half m2 mV2 square, but finally the kinetic energy has, so this is Ke I, and Ke final is, that is, so okay, the Ke final is this thing, this Ke final is half m V0 square plus half m V0 square. That means so V0, so this is Ke final, and if we put that this thing, so that will be, so what is the change in the kinetic energies? That means half m is common, so we can take half also common. So basically we will get V1 square plus V2 square and then minus 2 V0 square type thing, that is initial minus final. So half m will remain common and this will become V1 square plus V2 square minus twice V1 plus V2 whole square by 4. So this will become half m and this will become V1 square, suppose half, so we can write that minus, So this will become my V1 by this one. So this will become something like this: V1 square plus V2 square minus R2 we can take common, and then this becomes 2V1 square 2V2 square minus V1 square minus V2 square minus twice V1 V2. So this will become, so inside quantity can be written as something outside then V1 minus V2 whole. So therefore this energy is always positive. So that means initial kinetic energy is always more than final kinetic energy. Similarly, now I give one example of say some oblique contact. Suppose there is a rigid floor. Now a ball is hitting here at phi theta angle from normal. It gets reflected. Now if there is a perfect elastic collision, then in that case it will get reflected at the same theta. Why? Because in that case the that velocity of approach and the velocity of this one, so magnitude should be same. So therefore naturally the theta. But however in the other case, that if you know that E is not equal to this one, so then the velocity of separation should reduce, and therefore it will that go at something like this. So therefore this angle may be something phi, and where phi will be less than theta, say more than theta. In this case phi will be more than theta. So therefore if a small ball hits that perfectly smooth rigid surface, in that case the that like light, it gets reflected, just like light get reflected, in the same way it gets reflected, and otherwise that this is the thing. So this is one example of that oblique impact and about this thing.